Hello, this is Ashley, and this is my lab report for Lab 3. So, the purpose of this lab is just to observe the calculated orbits of an object moving around a black hole and other planetary bodies. And the main principle we use is the law of gravitation, which you can see the formula on the left. It's described there with the gravitational constant listed on the bottom. And on the right is a picture of an orbit with the direction of the force of gravity, which always points towards the source. And then we're also using Newton's second law, which deals with F net perpendicular and F net parallel and how they add to get F net. So this mainly deals with part one of the lab, as I will describe in a second. And the arrows in part one kind of just show how the components change while an object is orbiting a black hole. So you can see the three arrows on the top image. Again, that deals with part one, and then the orbits on the bottom deal with part two. So a force that is exerted on a planet is reciprocated onto that planet and any other surroundings. And then the parallel and perpendicular components of F grav on the system always point towards the center of the kissing circle, and they combine to get the total net force. So this is the code for part one. It's a lot of lines. Basically, we're finding FNet parallel and just FNet in general, and then using that to solve for FNet perp, kind of just an easier way. FNet perp does equal mv squared over r. However, if we just find the actual net force and subtract the parallel force, then you just get it by default, and it's just easier that way. And using that, we're calculating the mass of the black hole. And it obviously changes. So it's in every iteration changing based off of what FNet perp and FNet parallel are in the orbit. And then we edited the arrows to show FNet and then the parallel and perpendicular components. So that's that. Then in part two, it's a little bit more involved with the law of gravitation, basically finding the r vectors, their unit vectors, and the magnitudes, and plugging that all into the big negative gmm over r squared formula times r hat. And then updating the velocity, updating the position, all these iterations will eventually yield the graph on the right. And then I had to just experiment with the x and y components of the speed to get an orbit that kind of goes on for a while and that doesn't crash into the moon. It's not a figure eight, but it's fine. So FNet perp changes the direction of motion while FNet parallel changes the magnitude or the speed, magnitude of the momentum. The arrows show that the system speeds up when the FNet parallel is in the same direction of motion and slows down otherwise. And the FNet parallel is that small magenta arrow. An object that exerts a force on another object experiences an equal and opposite force from the other object, as shown in the orbit of the spaceship, which is that magenta trajectory. It is influenced both by the moon and the planet, but also exerts an equal and opposite force on them. But it isn't shown that much because the moon is just and the planet are just so many times larger than the spaceship. So some error is that obviously I had to trial and error like what speed would give a perfect figure eight. Obviously I did not figure that out. As you can see on the bottom image, it's not a perfect figure eight at all. But it's fine. The quantity would be almost impossible to figure out just experimentally. So that's kind of just the only source of error that I could find. If there was an error in my code, it just wouldn't run. So yeah. So, kind of discussing how net force is just different from the rate of change of momentum. It might seem that they're the same because you have dp or del cp over dt, which is time. So you might think it's like a rate. However, I think of net force more as kind of how an object is moving and how their components are changing rather than a rate. So yeah, we're kind of focused on, well, by what quantity is the magnitude of its momentum changing, and then how is its direction changing using perpendicular and parallel components respectively. And so if you have in a system a black hole, a star, a planet, and a moon, you just have to take into account all of the gravitational forces, and then using Newton's third law, that principle, apply them to each other in equal and opposite force, because if you only have like one of those pairs, it's not going to be an accurate depiction of the actual forces that are acting on each object in its orbits. So I think that the black hole or the planets interactions would definitely dominate the whole model if we had time and if we could do that. Thank you.